Grignards, and fun stuff like that. Any questions before we get busy? Hello. All right, the chapter on ethers isn't really complicated, isn't really long. That's because ethers in general don't do very much. They don't. They're pretty much an inert functional group, with the exception of the cyclic ethers. They can do some reactions, but otherwise not too much. Basically, an ether has organic groups on both sides of an oxygen. This is diethyl ether. Diethyl ether is the ether of anesthesia. Old time, but this was the one that was used for anesthesia. This is methylphenyl ether. This is tetrahydrofuran, a very popular, very useful solvent. Furan itself looks like this. It has two double bonds, oxygen in the ring. What is unique about this? When you look at this, what pops into your head? How many pi electrons do we have? We have 2, 4, and 6. These guys are orthogonal to the ring. These guys are pi electrons. They're up like this, just like these. So this is aromatic. Remember that. So this is furan. Tetrahydrofuran, you simply reduce the double bonds, and it looks like that. That's a very nice solvent. This is ethylene oxide, an example of an epoxide. The word ethylene, you may recall, is a trivial name for ethene. Ethene is just a 2-carbon alkene, and you react it, and you introduce an oxygen, make a 3-membered ring, and so it's called ethylene oxide. This type of compound is the one that we will have the most reactivity with in terms of ethers. When you want to name them, there are 2 basic ways, and they're both legal. You can look at what's on either side of the oxygen. Here we have ethyl group on both sides. We could call this diethyl ether. Here we have a phenyl group and a methyl group, methylphenyl ether. These are trivial names. We can also name it as a parent chain. In this case, it'd be 2 carbons, so it'd be an ethane. As an alkoxy substituent, so this would be like ethoxy ethane. Let's go ahead and look at some examples and see if we can figure out how to name them the hard way. For our first compound here, we have a 3-carbon main chain on both sides, but this has a methyl group sticking up, and that gives it the priority because it has the most carbons. So our main chain here is going to be this guy. It's a prop, and it's got a methyl group right here, so it's a 2-methyl propane as our parent. So our parent is a 2-methyl propane. Now attached to that, we have this thing. It's attached at carbon 1. And this thing would be a propoxy. So when we string this together, alphabetically, the methyl has to come first, then the propoxy, so it will be a 2-methyl, 1-propoxy propane. Now you can also just look at it and say, this is 2-methyl propyl, that's this half, propyl, that's this half, ether. You'll see it both ways. Again, ethers are not a big-time substituent, so not a whole lot to worry about here. Here we have the 2-methyl propoxy on both sides. So again, one of these is going to be our parent chain. That means this substituent on this side is going to be a 1,2-methyl propoxy. So we're going to have a 2-methyl propane as our parent, a 2-methyl propoxy as our substituent, attached to carbon 1. So 2-methyl, 2-methyl propoxy, propane. Or you could simply call it di-2-methyl propyl ether. Just like diethyl ether, di-2-methyl propyl ether. Any questions? On the exam, you're probably not going to see much in the way of ether nomenclature unless it's fairly simple. Here we have 3 carbons and 3 carbons. You have to choose a parent here, and IUPAC tells us that you want to choose the most complex chain. They both have the same number of carbons, but this one has a side chain. So this is going to be our parent here, a 2-chloropropane. And to this, we simply have attached a 1-propoxy. Chloro is going to come first in the name, then propoxy. And it would look something like that. 2-chloro, 1-propoxy propane. And finally, let's look at this guy. We have 3-carbon parent on both sides, but this has a carbon. Remember, this is organic chemistry. Carbon counts. Okay? Carbon is the most important. So this is going to be our parent here because it has the most carbons. So this is a 2-methyl propane. And on this side, we have a propane with a 2-chloro. So this is a 2-chloropropoxy substituent attached to a 2-methyl propane. And again, it would look something like this. Any questions? Once again, you will probably see a fairly simple nomenclature question or two on your next exam and or the final if you take it. But it's not going to be a major sort of focus. All right, ethers in general. We have an oxygen in the middle and we have 2 carbon compounds on both sides. The bond angle here isn't quite the tetrahedral angle. It's spread out a bit because you have the 2 bulky groups. It's about 112 or so. And remember, always remember that hanging down here, we have the unshared pairs of electrons. When ethers undergo reactivity, they're probably going to undergo because they're going to get protonated or something on this pair. That's what gives it its inherent reactivity. Now, diethyl ether is probably the big-time solvent. You probably used it in lab last semester. We haven't used it yet this semester. You can make it industrially by simply dehydrating ethanol, so sulfuric acid, pulls out the water, and you get diethyl ether. It boils at like 35 degrees centigrade, so very low boiling. It has an extremely high flash point. So it's very, very flammable. It's a difficult solvent to work with. And to make it all even more difficult, ether reacts with oxygen initially to form a radical. Now, if you look at this radical, what do you say to yourself? It's a resonance stabilized radical, isn't it? So that's why it forms on this carbon, and that's why it's, I guess, fairly easily formed. But the problem is that once you form this radical, if you have oxygen around, this will react with another mole of oxygen and will give you what's known as a hyperperoxide. Now, hyperperoxides tend to form in cans of ether that have been opened, that people were not real careful with about leaving them open so oxygen comes in. And there's typically just a little bit left in the bottom of the can. And it's an incredible contact explosive. Now, ether itself, very flammable, boiled at 35, et cetera, et cetera. So this is a real problem. Anytime you use ether, you have to make sure that, first of all, you have a full can. If you ever have to use ether, make sure you're the one opening the can. Because if it's been sitting out for a while, you can get this stuff, and this is not fun. This is really bad stuff. All right, how do you make ethers? Well, the guy named Williamson got his name tagged on this, and it's the simplest reaction in the world. Nonetheless, he's famous for the Williamson ether synthesis. All you do is take an alkoxide of some sort and an alkyl halide. You can have anything here with a decent leaving group. We'll talk about that in a second. But here we have methoxide. All that's going to happen is the oxyanion will attack the carbon, SN2 reaction, and virtually quantitative yield of the corresponding ether. Williamson ether synthesis is very simple. The alkoxide displaces the leaving group, and you make a new bond. Any questions? Well, let's do some. Go ahead and quickly jot down the products for these three Williamson ether syntheses. Remember, the alcohol attacks, the alkoxy attacks, leaving group leaves, and you make a new bond between the electrophilic carbon and the nucleophilic alkoxy. For our first one, the oxyanion is simply going to attack the carbon, and the bromine will leave. When that happens, we have a new bond between the oxygen and this carbon, and we would form benzyl methyl ether. Any questions? Our next one is just going to be pretty much the same. Phenol anion is going to attack the CH2 here. Bromine will leave. We'll get a new bond between the oxygen and the CH2. And will look something like this. Now our last one here, as you look at the reactant, I hope that you recognize the O-tosylate group. You should have talked about that in 234. This is a tosylate ester, toluene sulfonic acid ester. Looks something like this. Here's the R group, here's the sulfonyl, and there's the toluene part. If the R happened to be a hydrogen, this would be toluene sulfonic acid, which is a very strong acid. That means that this whole chunk is a beautiful leaving group. So you can easily break this bond. This half is what's referred to as a tosylate, O-tos, sometimes just TS. This half is the tosylate. And you break your bond this way, and this whole thing, this is the anion of toluene sulfonic acid. Very, very good leaving. So kind of think of it just as a halogen or something like that. To make this very simply, all you do is take an alkoxide of some sort, toluene sulfonyl chloride. The alkoxide attacks, chlorine leaves, and you get the ester. Very, very common leaving group. Again, it's abbreviated OTS or OTOS, tosylate is what it stands for. All right, so just regard this as a darn good leaving group. What's going to happen is the same thing. The alkoxy is going to attack the carbon, the tosylate is going to leave, and we're going to form the simple ether. Any questions? Now there are a couple ways, other ways, to make ethers besides the Williamson synthesis. If you think way, way back into the days of 234, there was a reaction that you did where you took an alkene, mercury 2 acetate, followed up with a borhydride reduction. This gave you an alcohol. It had Markovnikov regiochemistry, but the neat thing was that this had no rearrangement. So you could do Markovnikov hydration without having to worry about rearrangement. Well, instead of doing this entire reaction in water, if you simply do it in an alcohol, the nucleophile here is going to be methoxy, not hydroxide, and you're simply going to make the ether. So it's exactly the same reaction. Again, you get Markovnikov regiochemistry. You don't have to worry about rearrangements. Very nice, very sweet reaction. If you recall the mechanism, it looks something like this. In step 1, mercury 2 acetate will add to the double bond. It will form the mercury equivalent of a bromonium ion. Remember him? Well, this is a bridged ion. Basically, the mercury is sitting on this pi system. As it sits on this pi system, it becomes, both carbons here become very reactive. The carbon that can bear the most positive charge, which is the Markovnikov carbon, this is slightly more positive than this guy. So the second step, alkoxide, methoxide will attack, and you get your stuff. Now to get rid of the mercury, you have to dump in the borhydride, but you wind up with the ether. Once again, Markovnikov regiochemistry, A really nice clean reaction with no rearrangement. Any questions? Classic 234 chemistry. All right, the most interesting of all the ethers, I suppose, is the epoxide. Now we saw that with ethylene oxide in one of our first slides. If you take an alkene in the presence of a peracid, peracid basically just has one too many oxygens. This is an oxygen atom donor. And it will react with the alkene pi system to form the oxirane, which is also just called an epoxide. This is really neat because this is a highly strained ether. And because it's so highly strained, you can actually do nucleophilic reactions on this, just like we saw with the mercurinium ion, actually. So nucleophiles can come in backside, get ring opening, and you can make lots and lots of functionality. The peracid of choice these days, you can still use stuff like peracetic acid. Yeah, that's fine, that works. A really nice one though is what's known as MMPP, magnesium monoperoxyphthalate. So if this were just acids on both sides, this would be phthalic acid. If one of them is a peracid, magnesium salt, this is just a really nice reagent to work with. Nicely soluble, easy to get rid of, and the whole reaction just works really well. Quite often you'll just see alkene plus MMPP. Remember, MMPP means peracid. Any question? Well, there's a fairly brutal way to make an epoxide, aside from a peracid. Again, think back into the old days of 234. If you took an alkene, an HOBr, so that's hypobromite. Basically, that's bromine and water. That'll work. You can also do N-bromosuccinimide in water DMSO mixture. Fairly nice reaction. What happens here is we're going to add the hydroxyl group to one carbon and the bromine to the second. This goes through a bromonium ion intermediate, and we wind up with what's known as a hypohalite. So OH on one carbon and a halogen on the adjacent. You can do it with HOBr or HOCl. Both of them work nicely. Now, if you take this stuff and you treat it with base, you can get an internal SN2 reaction to occur. The internal SN2, we're going to make the oxyanion here. Our stereochemistry is trans, so we're going to make the oxyanion. It's going to attack, and the bromine is going to leave, all in the same molecule. There's our oxyanion. It simply attacks, bromine goes, and presto, we have made the oxirane, or epoxide. A little more brutal, perhaps, than the reaction with MMPP, but this reaction works fairly smoothly. So any question? You see the 234 chemistry comes back to haunt you over and over again. Let's go ahead and draw some of these out. Make sure we can figure out exactly what these epoxides are going to look like. Now remember, when you do a peracid addition of an oxygen atom to the alkene pi system, all in the world you're doing is taking your double bond and you're sticking an oxygen on top of it. Now sometimes people have trouble envisioning this, but just think of this as your styrene, and now we're going to put the oxygen right there, and it's going to look like that. It's called styrene oxide. With our next one here, once again, we're going to put the oxygen on top of this pi system. Now, because it is a single oxygen, both bonds to this must be on the same side of the molecule. Always make sure you remember that. So these two are cis, and this, of course, is cis. In our last example, we have an alkene, and we are reacting it with HOBr. And as a second step, we're doing sodium hydroxide. Now, HOBr, think 234, we're going to have Markovnikov regiochemistry with respect to the hydroxyl group. So, bromine will add to give a bromonium ion. Hydroxide anion will add to the most stable carbocation center, and you will get this tertiary alcohol. So this is our most stable carbocation, and here's our halogen. Step 2, we dump this into base. When that happens, alkoxide will attack, Br minus will leave, and we'll get our epoxide formed right here. And there it is. Now, epoxides are a little odd to draw, odd to think about, and sometimes people have difficulty drawing structures like this, envisioning the products. So just work about it. Think about it. All you're going to do is put an oxygen on top of the pi system of your alkene. Any questions? Well, I said that ethers were basically a boring functional group. Epoxides will undergo reactions, that makes them neat, but most ethers don't do much of anything. About the only real reaction that you can do with an ether is to split it in half. If you take HI, hydroiodic acid, boiling water, so it's not gentle conditions at all, what's going to happen is, step 1, the strong acid is going to protonate the oxygen. When you protonate the oxygen, that makes that a very good leaving group. So here, this group could easily leave as either methanol or tert-butyl alcohol. It's a good leaving group. It's an alcohol. Step 2, you have I- floating around in solution. And iodide anion is a decent nucleophile, but it's big. It's a big honking thing. It is going to attack the least hindered carbon, because it's got to get in there, doesn't it, to do an SN2 reaction. This is a tertiary center. There's no way iodide is going to work its way in there. This is a nice, happy little methyl group. Iodide will attack the methyl. When it does, it plucks it off, and you wind up with the corresponding alcohol and iodomethane. If you think about the Williamson ether synthesis backwards, this is the same thing, isn't it? Alcohol anion plus alkyl halide would give you a. So this is just reversing it. Conditions are very forceful, again, boiling HI. Not a great reaction. Any questions? Now, everybody's favorite ether, as I've said many, many times, is the epoxide. The epoxides undergo a plethora of reactions. These are all going to be ring-opening reactions. A nucleophile is going to attack at the least hindered carbon, so the easiest to get to. When it does, it's going to push this ring open and form a new bond. You can do this in boiling water and make a 1,2 diol. Now, think about this. We're going to be attacking this backside, aren't we? SN2. So that means these two hydroxyl groups must be trans to each other, opposite sides. HX, protonate this thing, X attacks, also trans-steric chemistry. Alkoxide, we can take a good anion. If it's really strong, it can bump in here, kick this out, and make the alkoxy alcohol. Grignards, our friend Grignard. Remember, a Grignard behaves as a carbanion. The carbanion can attack one of these carbons, and again you wind up with an alcohol. And finally, lithiol. What did lithiol do? Lithium aluminum hydride donates an H-. If you donate an H-, it could attack one of these carbons, and you simply wind up with an alcohol. Now we're going to do these all one at a time. It's just an overview. But they're all essentially the same basic mechanism. The nucleophile will come in, attack the least hindered carbon, ring open, and just simply add your nucleophilic agent. So let's start off with simple hydration. If we take our epoxide in the presence of strong acid, we're going to protonate the oxygen. This is equilibrium, but there's a little bit that's protonated. That makes this a wonderful leaving group now. Nucleophile, in this case, water or hydroxide, will attack at the least hindered carbon. And again, you get the trans 1,2 diol. That's important to remember, because remember way back in 234, what happens if you take an alkene and you react it with alkaline permanganate? You form a 1,2 diol, and the stereochemistry is cis. So that gives you cis stereochemistry. The oxirane gives you trans. That can be important if you're trying to plan aldol synthesis. HX, same thing. Strong acid, protonate the oxygen. We have X minus as our nucleophile. Once again, it's trans addition to give, what is this? Oh, by George, it's a halohydrin, isn't it? We saw this going backwards. If you treat this with base, alkoxide attacks, and halogen leaves. And you're back where you started. Alkoxides. You need a fairly brutal set of reaction conditions to do this. You're going to start off with an alkoxide and wind up with an alkoxide. Equilibrium-wise, this isn't great. I mean, you can easily see how this can reverse. The oxyanion coming back, kicking out OR minus. So you need a fairly hefty nucleophile. High concentration, fairly rough conditions. Finally, quench it in acid, and you trap the product. Our friend Grignard, remember a Grignard reagent, the alkyl group, or aryl, or vinyl, or whatever it is a partially anionic carbon. As such, it's a wonderful nucleophile. It will simply attack the least tender carbon. We have an alkoxide, work it up with acid and water, and we wind up with an alcohol. And finally, our friend lithium. Now, lithium aluminum hydride. We talked about this in the chapter on making alcohols. This is H minus. H minus is going to be our nucleophile. Going to stick on as an H minus, work this up in aqueous acid, and again we have made a simple alcohol. Now when I say this is an epoxide, something goes off in everybody's head, right? You've all used epoxy, right? That's what this is. How do you make epoxy glue? It's going to be the same basic chemistry. There are lots of things that are used in nucleophiles. One of the classics here is to use triethylene tetraamine. Lots of amino groups. The amino group is a decent nucleophile. It will simply attack the least tender carbon. We'll get ring opening, and we wind up with something like this. Now we still have 1, 2, 3 amino groups, don't we? And those are going to react with more epoxides and do the same thing. This is how you get a huge cross-linked web of organic molecules, and that's called epoxy resin. Now they all differ a little bit in terms of what you have attached to the epoxide itself, but the chemistry is basically the same. You can do a ring opening, make something, and then cross-link the heck out of it. Any questions? Well, let's do a couple reactions then. Whenever you see a reaction like this, you want to think two things to yourself. First of all, what is your nucleophile? And secondly, remember this must go to the least hindered carbon. So you have to look at the whole molecule and decide where it's easiest to get in there. Here we have isopropyl magnesium bromide. That means that this carbon right here is basically anionic. This carbon is going to be our nucleophile. It's going to attack our epoxide. Now we have two carbons in our epoxide, styrene oxide. This is a CH2, and this is the benzylic carbon. Now this is a real toss-up, actually, because benzylic things are just really, really good at doing like SN2 reactions. They really are. But the phenyl ring is pretty big and ugly. This is just a nice, happy little CH2 sitting out on the corner. And what's going to happen is the carbanion is going to attack at this center, and we'll wind up with this alcohol. Our next reaction, we have an epoxide and we have aqueous acid. So we say to ourselves, okay, step one, we're going to protonate the oxygen. Fine, we can do that. And then water or hydroxide is going to attack, and we're going to open up and make a 1,2-diol. Since it's 1,2, you really don't care which carbon is going to attack. Obviously, this is the least hindered. This is really crowded. The one thing that you have to remember to show in this type of a reaction is your stereochemistry. Stereochemistry is going to come back to haunt you. You have to show that the incoming hydroxyl group and the oxygen from the epoxide are trans to each other. Now we have a 6-membered ring. We could use wedges, or we could be more sophisticated and draw it out this way. Diaquatorial hydroxides, they are trans to each other. Our final reaction here, we have a simple epoxide with ethoxide as our nucleophile. So the oxygen is going to attack the least hindered carbon, and we're going to make a bond. This is going to be an OH. Clearly, this is a very crowded carbon right here. This is a simple CH2 group. That is where the attack is going to take place. Alkoxide attacks here, work up with aqueous acid, and we make this compound. Any question? All right, this next problem is actually straight off of an old 235 exam. It was the final exam, to be honest. Here we have an alkene, and we have two 1,2-diols. The question is, how do you make each of these stereochemically pure? Real exam question. It pulls upon everything you know from 234 and 235. All right, the key question here is, what is the relationship of the two hydroxyl groups to each other? Are they cis or are they trans? I mentioned just a little bit ago that if we had alkaline permanganate, we would make a cis 1,2-diol. But if we did an oxirane followed by a ring opening, we would have a trans 1,2-diol. So the real question here is, in which of these are the OHs cis and which are trans? Or are they both the same? Now that's a neat question, isn't it? Let's start off by converting these little projections into sawhorse. Remember sawhorse? A sawhorse is kind of neat because what you're going to do is kind of look down this bond and put groups sticking up and down the way they're shown in our projection. So in this one, just think about it. We have a phenyl sticking up and a hydrogen up, hydrogen up, OH up, methyl and hydroxyl are down. So the sawhorse for this guy would look something like this. We'd have phenyl ring up, hydrogen up, phenyl up, hydrogen up, hydroxyl up, hydrogen up, up and up. Everyone see that? This guy. OH, H up, OH, H up. So phenyl and methyl are both down. Both hydroxyls up, phenyl and methyl are down. So we have our sawhorse projections. Now, if we look at our starting alkene, what's the stereochemistry on our alkene? Well, the phenyl group and the methyl are trans to each other, right? They're trans. So what I want to do is rotate around this thing somehow so that my phenyl group and my methyl are on opposite sides. That is, as if they were trans, right? Now I can do this here easily by just rotating the methyl up a little bit, this hydrogen down, this hydroxyl up. Something it would look like this. Now let's watch it again. All I did is move the methyl up a bit, OH group up, hydrogen down, and now you can clearly see that these are trans. Now you look at it and say, okay, I got my phenyl and my methyl trans. What's the relationship for my two hydroxyls? This one is pointing up, this one is pointing down. What is that? That's trans, isn't it? How do we make a trans 1,2-diol? With peracid followed by aqueous acid. Hydroxyl groups are trans, MMPP, followed by aqueous acid mortar. Hydroxyl groups are trans. Now to make this easier to see, I'm going to rotate this guy so it looks like this. So phenyl and methyl, same positions. Okay? That makes it easy, right? So I have to rotate the phenyl up this way, puts the hydroxyl up here, hydrogen down. Phenyl up. Hydroxyl is over, hydrogen down. Just like this. This one, I'm going to have to move the methyl group up a little bit, putting the OH up here, hydrogen down. And now our basic backbones are the same. So now, what's the orientation of our methyl groups? I'm sorry, the hydroxyl groups? Are they trans? No, they're not. They're on the same side of our ring plane here. This is a cis orientation. And how do we make a cis 1,2-diol? We think way back to the good old days, and we do alkaline permanganate. Any questions? Now, once again, I will say it, ethers don't do much in the way of chemistry. You can make them, you can open an epoxide with a nucleophile, you can reverse it with HI, but they don't do a whole lot of chemistry. So, aside from your basic epoxide nucleophile questions, that's really what you need to know. But there is one other really neat thing about ethers, and this has to do with what are known as cyclic ethers. Turns out you can fairly easily make large ring cyclic ethers. 12 crown 4, 15 crown, 18 crown, 21, 24. That has to do with the number of atoms in the ring. Now, first of all, just looking at these things, that's kind of neat, isn't it? Just they're kind of neat looking molecules. But the thing that is really neat about them is that they have a hole in the middle, don't they? Now, what do you do with a molecule with a hole in the middle? Especially if you have Lewis bases all around the outside. Well, you stick the Lewis acid in the middle. And it turns out that 12 crown 4 can easily accommodate a lithium. 15 does sodium, 18 does potassium. And it does this very specifically. Let's look at 18 crown 6, that's our classic. 18 crown 6, we have 6 oxygens around. These are Lewis bases. And we can stick, this is what it looks like. Again, here's all of our oxygens. We can stick a potassium exactly in the middle of this hole. Now, remember when you have an ion in solution, it is solvated, isn't it? Solvated because it's surrounded by water and stuff like that. That means that you can't really dissolve potassium in an organic solvent because there's no water to solvate it, right? But If you dump in some 18 crown 6, this will wrap around the potassium. That makes this entirely organic solvent soluble. So you can put a potassium salt in an organic solvent. That's what it looks like in real life. It's just beautiful, the way it just kind of sits in the little hole there. And it just, again, it totally solvates your potassium ion. So if you want to do an SN2 reaction, say with potassium bromide, you need the bromide in solution and the potassium. Well, bromide is easier than potassium. So you dump in some 18 crown 6, goes in solution, you have a fabulous Br- nucleophile. Now, organic chemists weren't the first to think of this. Turns out there's an antibiotic, naturally occurring antibiotic, called validomycin. And this is what it looks like. It's a big chain of amides and esters all together like this. The way this thing sets itself up, the amide moieties here all point to the middle, and the esters point off to the sides. This, it so happens, exactly fits a potassium ion. So here's all your amides pointing in, just like 18 crown 6. Potassium in the middle. Why is this an antibiotic? Well, living things, including bacteria, have membranes, right? And they set up a membrane potential by segregating ions on one side or the other. This is soluble in an organic solvent, which means that's a membrane. So this stuff just flows right across the membranes, destroys the gradient, and the bug dies. Kind of really neat stuff. Any questions? Yeah?
As you get bigger crowns, do you just continue down? As the crowns go up or down, do you just continue down the first group of reactive?
Well, we're pretty much, let's see. We've done through potassium. I actually don't know. Rubidium and cesium might fit in the next couple. Yeah, they should. Yeah, I mean, that's really neat. That's it's kind of, it really is a neat concept. All right. Let's talk a little bit about spectroscopy. Remember that from your last exam. If you look at 18 crown 6, what would this C13 spectrum look like? Now remember, what question are we really asking? We're really asking how many types, unique types of carbons are there? It's a symmetry thing. Well, as you look around, we have a CH2 and a CH2. Are they different? No, in the simple NMR world, they're not. This one is next to a CH2 and an oxygen. This is next to a CH2 and an oxygen. They're pretty much the same guy, aren't they? So my prediction would be one type of carbon. But how about the proton NMR? We've already decided there's only one type of carbon, right? There's a CH2 next to a CH2. Is it split into triplets? C13 looks like this. All of these are exactly the same. We get one peak, one type of carbon in the C13. And the proton NMR, well, even though this is a CH2 adjacent to a CH2, we get one single peak. Why? Simple thing about proton NMR. If they have exactly the same chemical shift, if they're exactly the same in the C13, we have no splitting. If they're exactly the same, there is no splitting. So a fun exercise in simple. Any questions? All right, well, directly underneath oxygen on the periodic table, of course, is sulfur. And sulfur wants to do everything that oxygen does. So instead of ethers, they make sulfides. Sulfide is simply the sulfur equivalent of an ether. Once again, not a whole lot of chemistry goes on here. This is a fairly inert thing. Sulfides smell. Remember we said that about thiols. They stink just the same. Nomenclature-wise, we're going to use sulfide instead of ether. Instead of alkoxide, we could use alkyl thiol. So ethyl, methyl sulfide, methyl phenyl sulfide. Here we're labeling this as a derivative of benzene with a methyl thiol group. Again, a methyl thiol, propanol. We're not going to do nomenclature of sulfides on an exam, but just remember it's the same basic concept as ethers. How do we make it? Well, we could do the Williamson sulfide synthesis, can't we? Exactly like the Williamson ether synthesis. S minus is a nucleophile, a darn good nucleophile, by the way. Attacks an alkyl halide, SN2 reaction, and we make the sulfide. Going back here to our chapter on electrophilic and nucleophilic aromatic substitution, we pointed out that for nucleophilic aromatic substitution, sulfur was a very, very good nucleophile. This will displace the fluorine, addition elimination, and make this simple aryl sulfide. Any questions? There's one really neat thing that you can do with a sulfide. It can function as a nucleophile by itself, and it forms a stable sulfonium salt. Now, if this was an oxygen, this would be very, very reactive. Very reactive. It would have a lifetime of 10 to the minus 9 seconds. Sulfonium salts are stable as a rock. Sulfur has these d orbitals, you know. That makes all the difference. There's a biological version of this. It's called S-adenosylmethionine, SAM. There's our sulfonium salt, the adenine, ribose. This is methionine here, simply linked into the ring. S-adenosylmethionine can react with nucleophiles to liberate this sulfur. So kind of the reverse of how we formed it. So a nucleophile comes in, we liberate this half of the molecule, and simply transfer the methyl group. Biologically, this is a very, very important process. This is how you put genes to sleep. You methylate them. This is how you, probably, how you do long-term memory. You methylate things in your brain, the brain cells, and that changes the chemistry at the neurons. So it's a very, very interesting, very important compound. Any questions? You can also take a sulfide and you can oxidize it. If you oxidize it once with peroxide, you get a sulfoxide. It's actually a zwitterion, plus and minus. You can do it a second time with a peracid and make a sulfone. Sulfoxides are probably the best known. Dimethyl sulfoxide is an interesting compound. Has had a bit of a history in pharmacology. Dimethyl sulfoxide, so methyl group on both sides, is a fabulous solvent. It will dissolve everything. Everything. It is just really good. It's the sulfur equivalent of acetone, except it's better. Because it's a zwitterion, it can also grab ionic things and hang on to them. DMSO, dimethyl sulfoxide, is very soluble in biological membranes. If you take DMSO and put it on your skin, it just zoops right through. Right through. Problem is that it carries everything with it. Everything. Good stuff and bad stuff. It was, it still is used as a drug delivery system. So you have something in DMSO, put it on your aching joint, and it just sucks it in, and it helps. It's really nice. Again, the problem is that it's so good at doing that if you have any junk on your skin or any impurities, they go into it. You'll still see lots of people doing DMSO therapy for arthritis and stuff like that. One of the real problems with that is you put DMSO on. DMSO has a smell, but not super bad. But as soon as it gets in your body, your liver converts it to dimethyl sulfide. Dimethyl sulfide smells like 50 tons of dead fish. And it all comes out in your breath. So, not highly recommended. Any questions? Here's a reaction we don't know yet, but it's actually really cute. One of the neat things you can do with a 1,1-disulfide is reduce it away. We will talk about this reaction when we do ketones. But if you take a 1,2-diol, or in this case a 1,2-disulfide, react it with a ketone or aldehyde, you form what in this case is called a thioketone. It's a very stable sort of thing. It's really neat. With a diol, you would have oxygens here. Very useful compound, whatever. But the one thing that the disulfur version does that the oxygen won't is it will be reduced by rainy nickel. Rainy nickel is just porous nickel saturated with hydrogen gas. You dump in rainy nickel, and by George, everything disappears. So if you ever have a ketone or aldehyde and you want to get rid of it, this is a very, very simple way to do it. And it works very nicely. Any questions? All right, let's wind up this entire evening with a synthesis. That's always fun to do, right? This is organic. I'm going to give you benzyl bromide, and I want you to make this ether. Now in 235 we do syntheses. So, again, let's just think about how we do a synthesis. When you do a synthesis, you want to look at your product. It's okay to peek at the starting material, but just peek. But look at the product and then ask yourself a question. What is it? Well, it's an ether. How do I know to make ethers? Well, after today, I know several ways. I could do Williamson, alcohol anion, alkyl halide. That's simple, right? So you look at it, say, what is it? How do I know to make it? It's an ether. I'm going to do a Williamson. Then you look at it and say, okay, which alcohol would I need? And which alkyl halide? This is a grounded carbon. This isn't. Probably you want this end to be your alkyl halide. So you could do this by simply splitting this off and adding this as, say, bromomethane or iodomethane. The reaction would look like this. This is the alcohol we would need. Something like iodomethane, use sodium amide to make the anion, and do our reaction. That'll work. Now you sit back and you feel happy for yourself because you got this set right. But you have another synthesis problem, don't you? That is, how do you convert benzyl bromide into this alcohol? Well, how do we know to make alcohols? Starting with an alkyl halide. This should stand up and scream at you. Grignard reaction. If we do a Grignard with an aldehyde, we will make a secondary alcohol, right? So, this has got to be our alkyl halide, so this is going to be our Grignard reagent. What aldehyde do we need? It has to have 1, 2 carbons and a carbonyl. This is our Grignard half in red. The blue part is our aldehyde. Again, this was a carbonyl, there's a hydrogen and a methyl. This is simply acetaldehyde. Any questions? Let's do one more synthesis. I want to make styrene oxide. And all I have is 2-phenyl ethanol. So step one, you look at your final compound here, say, what is it? It's an epoxide. I know 2 or 3 ways to make epoxides. I can do peracid, or I can do halohydrin. Now I know the answer, so let's do halohydrin. What halohydrin would you need to make this molecule? Well, the OH would have to be bonded to 1 carbon and the halogen to another. That's all you need, right? That's a halohydrin. So we could do it this way. OH bonded to 1 carbon, halogen to the other. Stew it up in base, alkoxide attacks, bromine leaves, and poof, we have the epoxide. All right, how do we make halohydrins? We make halohydrins from alkenes. What alkene will we need here? We simply need styrene. React this with HOBr. Do our ring closure here with sodium hydroxide, and we've got our compound. Finally, how do we convert our alcohol into an alkene? Remember chapter 17. We had a very nice way to make double bonds using POCO3. That is, we made a chlorophosphate ester, which underwent a beautiful SN2 reaction. I'm sorry, E2 reaction. So how do we convert this to this? Simply POCO3 and pyridine. The pyridine acts as the base, do our intermediate ester, and poof, we have our alkene. There's another way we can do it. We talked about it today. We want to convert our OH into a very, very good leaving group. What was the good leaving group we talked about? Toluene sulfonate. So we could do this with tosyl chloride, followed by base, and again we would make our compound. Now there are 2 other things we can do here. Number 1, once we add styrene, why bother doing this? Dump in the MMPP, and poof, we're up here. That works, right? Or, starting with our alcohol, how could you go to this guy? Our bromine is on the benzylic carbon, isn't it? Remember allylic bromination? If we simply take N-bromosuccinimide, we will brominate at the allylic or benzylic position and get to this guy directly. See, the really neat thing about organic synthesis is that there are so many possibilities. There really are. That's what makes grading an exam so very difficult. because somebody could have some bizarre way to get from here to there that's totally right. Organic synthesis is just plain creativity.